So now coming back to the presentation, actually, I was thinking what topic I could present, and maybe you know that my background is very on kinematics. I'm very on the full-scale kinematics and looking at closed-form solutions, and I really like all difficulties that we have there are really more a pleasure than a difficulty. And but then I thought maybe to talk about topics that I think will be coming up in the next years more and more strongly, and that's why I entitled it Robotic Applications at the Human Interface. Of course, this topic is very, very broad, so I will just be tipping a little bit on it. I cannot cover everything, and I will be mixing a little bit of available information in the internet, and in particularly showing some things we are doing there, and which, in my opinion, really create enthusiasms for it. So we will come back to this picture at the center. So I will have a little bit of an overview, let's say, and then go into some details of what we are doing, but I'm not going to go into the all this complete mathematical details due to lack of time. Actually, the problem is, or was always, when you give the speech to somebody to talk about what they are doing, it's very risky because we tend to never be able to stop. So once we start talking, then we never stop. First, we are reluctant of talking at all, but once we start, we don't know when to stop. So when I'm putting together these slides, and I learned that we have 1 hour, then what happened is that say, well, let's put this inside, this inside, this inside. So right now, I'm afraid that the slides may be a little bit too much, so I will be maybe skipping the one or the other quickly. But it is recorded. You can then see it slow motion, and then you can see it in twice the time. So the idea is that I give you a kind of an overview of human-robot interfaces. Of course, much of this is known as cobots, but really there are other things that can be done. And as one example, I'm going to show our ride simulator that can be used for having the interface with the human to create motion sensations, but I will also talk about further applications and some conclusions. So if you look at robotics, this is already a couple of years old, but there was this search analysis by McKinsey, and they saw that among the 12 technologies that are going to be disruptive in the area of $1 trillion a year, one of them is robotics. Robotic tools with dexterity and intelligence, and including robotic surgical systems, and also robot processes and exoskeletons. So all this is at the interface between robots and humans, and we still don't have the big impact right now, but it's expected that this will grow. In my opinion, not so much due to intelligence, but much more due to tactile interfaces. So if you look at the current robot population, then we have about 66 robots per 10,000 employees in production. So this means that one robot per 152. And well, the key countries of robotics are in Korea and Japan and also Germany, and this is mainly because they're used very much in car industry. But as you can imagine, this robot pair population will grow if there is more and more activities that can be shared between robot and humans. And the evolution of these robots always started at the technical system. So this is the origin of the first robot, which you can see if you look at, Wikipedia or this history back in 1954. And so the first application was a very technical one. So for forging applications, where the robot was just a machine that was able to lift very heavy workpieces. And also, this is important to have in mind that robots are never introduced to kill human working places, but mostly they are introduced to relieve workers from very heavy work. And then this continues to develop. And it was interesting then that 7 years later, the next idea came to have a robot interface with a human, at that time just serving tea. So this is more or less the history. So you see, it took about 13 years from the first technical idea to having it at some human interface. Of course, today you would never allow a robot to work like that next to a person, because if this robot does a control error, then there will be a big injury. So we have to go through very, very severe safety measures before a robot can be near a human. And to me, it was interesting how this is developing now. And they invited me in 2017 to give a lecture for children aged 8 to 12. And I must confess, I was never, but since a long time, not so nervous about a lecture like this one, because I thought, if I don't keep this 500 kids happy, then this is going to be a complete fiasco. So I really had to think a lot what to do. And so I put this together, how times is changing. So I asked the children, who has already the robot at home? And you see a lot of hands raising. So it is already starting that this robot population is becoming more and more close to the humans. And also the control of robots is becoming more and more simple. One girl from this audience just came down, and then she learned quickly how to program this robot. So we have also important parts for having the robot at the human interface, that they must be much easier to handle and to control and so on. So there's a lot of work in this direction. And then what was most impressive at the end, I asked, do you have any questions? Well, they asked some questions, but this girl asked, how much costs such a robot for my home? So, and she was already planning to put her pocket money together to buy such a thing for herself. So we see that robotics is going to change a lot, and humans are open to having them. And the question is, what are interesting applications at the interface? And of course, this is a very, very broad field, as I said, and I just put some that can be used.
Andrés, we have a difficulty hearing you while the video is playing.
Right now. Used, let's say, in a broad industry. Then we have already cooperating robots, which kind of look a little bit like a human. And we have also already robots that are at the human interface, or helping people walking. This case, motion. So more or less the next.
Andrés, sorry to interrupt. Can you hear me?
More interesting can be in the future.
Andrés?
Yes.
Sorry to interrupt. While you're playing the videos, we cannot hear you properly. Maybe you can just shut down the speaker for the videos while you're playing the videos. There was a problem. As the video is playing, we could not hear you properly.
So did you hear the video?
We could not hear the video as well, so it was just not understandable sounds.
Okay, so then I must turn off the speaker, right? But then I cannot hear you. Okay. Let's see. So there will be not so many. Okay. We will not have too many with.
You can mute the videos while you're playing it.
Can I do it? In theory, but how can I mute them?
Well, it was, I think, at the right bottom corner.
This one?
The video that you played just a moment ago. Okay, yeah. Well, that's a media player, so you can just close it there. Yeah, that's it.
Yeah. Okay.
It
seems not to work anyway.
No. Okay.
Okay, no problem. Thank you. Thank you. Sorry for that. I check it here. Yeah. So also we have robotic systems for surgery, and they will be able to adapt to motions of the human. So this is something that is coming up. So in this talk, one thing I wanted to show two applications where we are currently working and one that we are planning. And what I found since long time interesting is to have ride simulators. Here, this is just a graphical overlaid picture. And so that we can have motions that have large tilt angles, which compared to normal vehicle simulators, which are on parallel platforms, are larger. And so we can have much more, let's say, rotation motion, like in a rollover simulation of a car. And here, very interesting applications come, because the question is, how does a passenger react to such situations? And as you can see here, this situation is very difficult, because if the test driver doesn't have the car under control, then some injuries will happen. So robots that can do this kind of motions without creating any risk of harm are, of course, quite important. So in this setting, very interesting interfaces arise between the control, the kinematic control of a robot and a human, because we have to also model the perception. So we want to model the perception so that the motion goes as close as possible to the target motion. Here we have this robot which is safe. So we have the German technical safety agency that cleared the system. And I must say that a lot of costs of this was just taking care of this safety systems. We are using here a roller coaster seat because we have cooperations with a roller coaster company, which are safe. They don't have shoulder belts, but here a hip belt, which is a patented belt, so that you can have turn up, down, and nobody will fall down. And this is a KUKA robot where all parts have been X-rayed, so to eliminate the risk of cracks. And once a year we have to have a complete inspection, so the robot can only be operated with this safety. And this is also an important, interesting issue when you have robots at the interface with humans, that safety becomes a larger issue. So as I said, we worked, I'm from dynamics and kinematics, and we designed a layout program for roller coasters. Here you see the real motion. Actually, this is not slowed down due to numerical slowness, but the roller coaster has the elevator in the loop. So the people go up and then they will hanging on top, screaming, and then they go down. And we use a complete dynamic simulation over the whole track to compute the accelerations at every seat. As you can see, the accelerations are not the same wherever you are, because maybe when the front one will be in another situation, combining centrifugal forces than the back one, and the velocity, of course, when you reach a point on a rail is not the same for the front and for the back seat. And so all of these are tracked, and then the task is to shape the geometry of this track so that the fun is there, but you don't violate acceleration limits, which are they are linear, but they are a combination of linear limit surfaces. And then all this is modeled by splines of fifth order, because we have to have also continuous rotations, and then the splines are optimized to the control point so that at no position these limits are violated. And as you can imagine, if one does a change at one point of the rail, this has influence much later flow down on the rail. So it's a really coupled global system. So this kind of coupled global systems are very typical when we have some applications at the interface with humans, because the change at one point can have influence on something happening much later. So for this, one has to design some tools for generating 3D curves, but not only curves, but also rotation. And we were working quite a while. Normally this is done by hand, so somebody is changing the shape, and then you can compute dynamics and put some virtual sensors, and then this is evaluated and is corrected. And for trajectory, you have geometry where the rail should be or could not be, the dynamics, what are they allowing accelerations or forces, and also the tracking, so that you have an idea how fast everything is processing with passenger number and so on. And so typically one wants to design these optimizers so that the engineer just creates a creative specification and the program smoothes everything. And so to do this intuitively, we designed what we call the spline joint. So coordinate system is moving along a spline, including rotations, and the task is to determine this reference frame for any the path coordinate. And by combining this to libraries, then we can put this together also for other applications. For example, in hydraulic machines, where one wants to have optimal tracking of the shovel, but with limited forces at the cylinders, and also with limited power limits of the complete engine, or also no slip conditions like with suction grippers. And so to give you an example, if you try to move what we call the general waiter program tablet with many glasses on it, then if you move it too fast or accelerate too fast, then the glasses will start to slip. So the question is, what is the optimal motion that one could achieve? And after optimization, one of course sees that the best one can do is to tilt first the tablet, so that when you're pulling, the accelerations become also normal accelerations. By this, the glasses will not slip, and then you invert it at the other hand. And maybe you have seen this also. I've seen this in Turkey, where the tablets are hang on chains. So more or less, this is the idea. So using this concept, you can move much faster. You see here, it's about 0.6 seconds. So it's 25% faster than moving with a horizontal tray. And the problem here is really very non-linear. So more or less, these black contours are the top and the low limit. So for example, you cannot stop moving. This is velocity, because if you stop moving in middle of the motion, then of course the things will fall down. And also you cannot move too fast, but these limits are not anymore linear. They're quite non-linear. And the challenge is that you accelerate as much as possible and you brake as much as possible. You know, maybe this bang bang. If you want to go as fast as possible from one to the other position, the best you can do is accelerate to the maximum and brake to the maximum to get there. But as you can see, these sequences are again non-linear, and more or less the task of the optimizer is to find the highest sequence of green and red curves, so that they just touch the limit. So because if you don't touch the limit, then you still have a little bit more room to get faster. But if you are too fast, as I said, maybe this can happen here, but much later, then this trajectory doesn't work. So these are also typical topics that arise in this robot-human interface. And for the motion simulator, the task is interesting, not the position or the force, but the acceleration. So you see here, acceleration is what EE means, the end-effector. So it's the perceived linear acceleration, let's say here more or less where the vestibular system is. And so the task is that this acceleration is as close as possible to the target one. A very interesting task for robotic applications. And so more or less during time you have these different target accelerations, and now you have to optimize the motion so that the robot is capable of doing these accelerations as close as possible during the motion. And of course, the problem is that the robot might have moved already too far, so it cannot hold anymore the acceleration. So you have to really optimize the global motion of the robot so that at each position you can get as close as possible to the target acceleration. Because if you just accelerate, of course, then like in a roller coaster, the car will be 600 meters far away, and the robot cannot do that. So we have this kind of optimization where we want to track as close as possible the target acceleration from the measured one, but we have everywhere limits. So the limits are the axis must be in some interval, the velocities must be in some interval, the accelerations must be in some interval. So, and also you have to define the global motion. So this is at the end quite a challenge. And we applied this kind of things in two applications. One is from a regional company here, the idea to use a robot to compensate ship motion so that a technician can step over, let's say, at wind parks, as offshore wind parks. And as you may know, offshore wind parks are not built for very calm seas, so they are built for wind. And when you have wind, you also have quite high waves. And then the question is, how do you get to this tower when you want to do some repairs? And here you see the idea that the robot more or less is doing the contrary of a normal robot. The robot is not moving the end effector, but it's compensating the end effector. And what you see here is one of the big problems that we faced in this application, namely, you see that the wrist is jumping because it's passing close to a wrist singularity. And while in normal robots, you have the emergency stop, which is a big red button that you have to place in every robot cell, which means in danger, press this button. In the case that you are compensating ship motion, if you have an emergency stop, then what will happen is that this robot becomes rigid, stiff, and then this cage is going to be bumped on the tower, like with a hammer. So we have to avoid, until any circumstances, that a robot ever runs into singularity or axis limit. Because if it does, the robot does emergency stop, and then the passenger is endangered. So actually from this, we looked at singularity, let's say, navigation concepts. We cannot avoid passing close to a singularity or in a singularity, which is normally the task to determine singularities, but we might be forced to really live with them. And so we must just avoid that the system behaves singular, but we have to get close to these singularities. So here something happened with the typos, but we are not to go into detail. So here we have a 6-axis robot, and in a singularity, more or less, you can imagine that 2 axes operate on the same target space, and then you lose, of course, 1 degree of freedom in the complete space. So more or less, this is what happens in a singularity. So you still have 6 axes that you can still control, but 2 are operating on the same subspace. Or the subspace can be a line or can be a rotation axis. Because 2 are operating only on a subset, then of course you must lose something from the 6-dimensional motion. And so there were some ideas already in the past. For example, the damped least squares method, the weighted ones, and then more or less what one does is that one tries to track as close as possible the target. This delta here is kind of error. Something happened here, I don't know what. And this should be q dot. And this should be the task velocity. So you try to be as close as possible to the task velocity, but you punish very high axis velocity. Sorry for that. Here you should have the axis velocities. So that means that your optimization tries to keep the axis velocities low. By this avoids singular motions, but still track as close as possible. But also this means that you will not be able to track very close if you are close to a singularity. And then for this, some error correction is applied where, sorry for that, the deltas are different symbols. Something just happened this morning, I don't know what. And then in this case, you punish this should be the error from the target motion. So let's say this is your target, this is the actual computed value of the interfactor, and then you punish when this is too far away. By this you can get some better properties. So another idea we introduced was to have the virtual revolute axis, which means that you introduce an additional joint which is not existing on a robot, but you put as in case of a redundant robot. And somehow the pictures now didn't work. I'm sorry for that. Here you see, for example, this here is a virtual prismatic joint that does not really exist, but it's just computed for a numerical model. And then when you prescribe some motion that is too far away when these axes are stretched, then the virtual axis will compensate for that so that you can reach the target position. And then in the application, what we do is we ignore this virtual axis, which does not exist, and just use the control for the real axis. By this, the control will always be smooth and will always be as close as possible to the target as can be. And because we are not going to details of the formula, I apologize here. It couldn't be followed anyway. But the thing is that we apply additional redundant degrees of freedom in a virtual model that will take care of compensating the limit situation, and then just use the real axis motion. And by this, we can always be as close as possible to the target motion and also to have a repeated situation. So one can weight how much one punishes when the motion is too far away. And here you can see the behavior. So let's say here we have a robot that is passing quite close to the singularity. And the weighted axis method will have a small deflection that is starting much earlier than passing this singularity. and also will be carried on more stream downwards. Of course, here we don't see so much, but if we look at the error, one can see that if we use this virtual redundant axis, what happens is that only at the points where we have this impossible tracking, you will have some small deflections, and also only in direction where you cannot reach them. While if one uses this weighted least damper method, what happens is that first of all the deflections become larger, and also that you spread these deflections on all other directions of the end effector, because of course due to this damping, then the whole end effector becomes shaking. So if we don't have the full singularity but have a small difference between them, then you can see even more clearly what happens. So when passing through the singularity, there must be an error, because the robot cannot track this. This is in direction of a locked direction. As I said, if your singularity, two axes are doing the same, so you lose 1 degree of freedom, and we now applied a deflection on this 1 degree of freedom. And you see that if you use this virtual redundant axis, what happens is that only when you pass through the singularity, then you have an error in direction of this locked motionless space. While if one uses this damped least square methods, what happens is that first of all you spread it on a whole space. You see also there was a translation here, not just a rotation. Here you just have a rotation about this point. And in the case of the robot approaching the tower, this translation deflection can be a problem, because then it might bump on the tower. But also that the deflections remain much longer, because this weighted least damper method is spreading this error by this velocity punishment in a function. So what my bottom line is that here, for example, you see a case where the circle, the target circle, cannot be reached by the robot about here. And if we use this so-called virtual redundant axis method, then the whole error is just concentrated, as I said, in the longitudinal direction, which cannot be achieved. And this virtual joint just swallows this error. No? While if you use this weighted least damper method, then what happens is that once you pass through this singularity, again, the robot will not reach. But as you can see, the error remains for much longer and might even oscillate to the other side, no? Because you have this kind of damping behavior and so on. So here we have a case where two singularities are reached at the same time, so you can become more and more severe on these issues. So at the same time, the robot is at the stretch position, and the head singularity is if the end effector is just on top of the axis, then of course this degree of freedom becomes free, the rotation about this axis, and this means that some others are locked. No? And here you can see again, if you use this virtual revolute axis, because we introduce an error, when you pass this, you have to leave the track, but it will come back quite soon again to the track. And if you use the weighted least damper method, then this oscillation is carried down, streamed down, as you can see here. Much later, still you have a big error, which is because you are doing a compromise between tracking accuracy and distance from the singularity. So at the end, I found this problem interesting, because once you start working at the interface, you get quite interesting kinematic problems. Now I have we'll go a little bit quicker. The perception is also a very interesting thing. So you have perceptions at the so-called vestibular system, but you also have perceptions on pressure, and this is called proprioceptive. And so a good model tries to use also the gravity. So by tilting this platform, the gravity will produce a sensation that you are accelerating in a transversal direction. And if you use this properly, then you can give to the person the feeling that he's accelerating this direction. But if you rotate too fast, then this will not work because you have the feeling that you are rotating. So there are a lot of work on this so-called washout algorithms, and it's interesting that it's still research going on. And we apply this to our robot we have in our lab. Here we don't have now voice, and this is a TV recording many years ago. You will see it on my hair color and also cut. So the idea is that here you see the system safety. Here we have the graphical CPU. Here is a screen which avoids that the passenger can put fingers inside the joints and then get the fingers damaged. We have here the safety belt, and you can imagine that you cannot run this kind of tests without safety clearance, almost at the top level, almost like an airplane. And this, of course, was done. And so the idea is that you create a sensation that you're moving in space by using embedded graphical systems and also the translation. And more to the end, you see here a little bit different hair color and cut, but always talking too long, so I'm trying to skip this. And this is one application we're looking at what happens in car rollover situations, but of course without creating injury risk for the passengers. So there's something that can be done in this direction, and there are a couple of systems in Germany around. Now I will show one other application we are currently working on, and by this I want to show how long it takes really to come from an idea to something working. This was an idea that I presented in the IFTON conference 2015, the year when I gave over the editor-in-chief position, in fact. And the idea is to use tactile robots to identify the joint axis of a human being, because it's important to know which is the real axis. Otherwise, the robots will be operating not in the real axis and creating some okay, got it. No, so these kind of systems are used for rehabilitation, but again, they are purely kinematical. And you can imagine if this axis don't coincide with the elbow axis, they will be generating some restriction forces. So this was the idea, to have a system that can be applied there. And very quickly, we work also in the dynamics of the body. So we have a library where we can model the joints and the muscle forces and all these kind of things. And for example, here is a simulation of the motion of the real bones. These are MRI bone segmentations using tracking data. And this can be applied also for, let's say, controlling platforms. Here was a idea to put a vertebrae inside, and also, well, we can apply muscle forces and then look how the system moves. But I must say that the computation of muscle activations is still a big open issue. How a human activates muscles for dynamical tasks is still not solved. But still, one can do a couple of things. For example, we use this simulation to predict a little better how medical people use different therapies. This was a project that was funded for 3 years. And we have to do a lot of very, let's say, fuzzy criteria that we need to put into machine learning. This also goes with interface between robots and machines. Here you see a more or less a graphical user interface for a digital act for people with stroke impairments, walking impairments. So one shows 3D videos, one shows the real videos, one shows angles. I can tell that if you look at cooperations with medical people, we engineers, we are used to really read such plots, but for medical people, they look much more to the whole picture. And so using these models, the idea was to identify an unknown axis, and the mathematics for that was that more or less we use this power iteration method that you might know. If you have a matrix A, one can prove that if you repeat multiplying the result by the matrix, so you get the higher orders. So if you take B times A, that's A times B, then you multiply against times A, then it's A squared times B, and so on. Then it can be shown that if you have a series of eigenvalues which are monotonically decreasing, so the first one is the highest, and you don't have two equal. In the case of two equal, it's a little bit more complicated. You have subspaces. That if you apply this iteration, you converge to the eigenvector of the highest eigenvalue, because you divide by the eigenvalue, and then all this becomes to the power k, and this is far larger than this one. If k is large enough, then this will tend to 0. So more or less, applying the same matrix over and over again leads to that your convergence to the eigenvector of the largest eigenvalue. So if you apply that to impedance, impedance means if you apply a force, what is the motion? Now, stiffness is if you apply a motion, what is the force? Or more precisely, motion increment and force increment. This is like a spring. But if you do it the other way around, then you ask if you apply a force increment, what is the motion increment? This is the impedance. And then, of course, the largest eigenvalue is the direction in space with the least restriction, the least stiffness. And if you have a slack arm, then of course the direction of the free joint will be the direction of the least impedance. But it is very difficult to measure this matrix or a stiffness matrix because it's 6 times 6 and you have many effects that are mixing. So the idea was to not compute this matrix, but let the body do this multiplication, but just by applying a force and looking at the resulting twist, where actually it's a wrench, force and moment. Then we look at the resulting twist, and then we apply this twist again as a wrench, of course, scaled. And then look at the twist, and then apply this twist again as a force, or force wrench, and then repeat that. And by doing this, we are actually carrying out this power iteration on the body itself. And then we expect that we will converge to the axis with the smallest impedance. So more or less, it's a very simple iteration where we just apply a force, look at how it's moving, then rescale this to a force and apply until we have convergence. And we tried this, of course, not on a human body, but first on a test rig. This is the axis that we want to show. And here we put this ring, which is elastically suspended, so that we can also have some relative motion. But because this is the axis of the lowest impedance, we expect that the control will go to the find this axis. And the result was that actually one can detect this axis with error of 5 millimeter, which is 1.6% for the position, and a direction error which is below 1 degree, which is 0.9% of orientation. So in fact, this works quite well, and so we started a project called Robotic, where we're using 2 robots to detect tactile the axis. And in contrast to existing systems which use more kinematical control, this would be an adaptive tactile control. Sorry for the German, but I guess you might understand it. Here it's more or less haptic determination of the kinematical knee axis using a robotic adaptive tactile system. And this kinematical axis is very important because it is not the same as the bone geometry. So the humans have different kinematical axis because you might know that the knee also does small translations. So the actual kinematical axis is changing over the flexion. And it's very important to know the real axis, for example, for hip replacement, joint replacement, to know which is the normal motion of the person. And one thing that we will be hopefully working is we're working on this concept is also robots are also used in a snake form. The snake form means that the robot is deformable, and there is the system that is used to reach some tumors that could not be reached before unless cutting here on the neck. And for me, it was interesting because we are cooperating here with Professor, the chief surgeon for the ear, nose and throat clinic in Essen. Is the long time it took for developing this. So you see how long it took to go from the first industrial robot to the first medical robot. And you know, the Da Vinci system, this is now almost for 20 years now cleared. And then this snake robot was cleared in 2015. And actually one of the more or less inventors of this was Professor Alan Wolf, who came from the kinematics community. And he was proposing this long time ago in the 80s. So it took quite a while so that this could reach the application. And well, this is the Da Vinci system where the operator doesn't look anymore as the body, but everything is done in telemetry. And this is the snake robot. And actually it's being used already. And it has clearance for colon operations, but also for head, neck and throat. And it has this patented idea that you can deflect the outer tube and then fix it, and then you can push the inner tube that creates the fixation. And then this system has on the two sides instrument channels, also for having video and light and so on. So the task here is very interesting because it means that the operator is able to do some more or less direction correction of the tip, and then the robot follows the task. And for me, this is also quite interesting, where we don't yet have results, but where we want to work in future in that direction. Very shortly, coming to the end, we were also working on different projects where we use IMU sensors at the foot and ankle to using this inverse dynamics models from robotics from the 80s, estimator for the joint forces. So more or less we project the mass of the body to this end effector motion, and from this we can estimate what are the forces during normal running to avoid injuries. Also, we are working with electrical colleagues, electrical engineering, using RFID sensors that can be stitched into more or less smart leggings. And by using this, they can be carried in normal life. So more or less, this can be tracked, of course, with all the data protections and so on. And then the medical people can have an idea how the rehabilitation is developing during their daily life. And one last thing we found very interesting is to use pressure foils to determine the location of bones within the body. And this was done in a PhD. Here, of course, you see more or less a garage version. And by using these pressure foils, we were able to determine bone position in sub-millimeter precision, which is much more precise than using skin arcers. So I'm coming to the end. Of course, there are many people to thank. There are also many funding to thank. And to come to the conclusions, I believe that, well, in one specific area, this ride simulator robot base has large potential of growth for many applications. I believe that human-robot interface opens many new application fields in medicine, but also in industry. And I believe that this robot interaction with the human interface will be a major area in the future, of course, as industry is starting to use them more and more. With this, I thank you for your attention. And if you have any questions, I'm happy to answer them. I think I used too much of the time now for questions. So anyway, thank you.